Chapter 24 introduces us to the electric potential, or voltage. So, let's imagine that we've got an electric field. The electric field's directed to the right, and we have some small positive charge Q. And I want to move my positive charge Q some distance in that direction. Now, the problem is there's a force due to the electric field on there. The electric force is going to be Q times E, which means I have to exert a force in the opposite direction. So I have to exert a force that's minus that in order to move at constant speed. Okay, now think about this. Is very much like when you had some mass M. We know that gravity exerted a force mg downwards, and I want to go some distance h upwards. So that means I have to exert a force equal to mg in order to move upwards at constant speed. Now, we know from physics 1 that work equals integral f dot dx. Okay. And so in the case I just gave you, then the work would be mgh. We know that work is equal to the change in energy. Okay, that's energy, not electric field. Now, if we're going at constant speed, so in other words, if my force that I'm applying exactly balances the external force, that means the change in kinetic energy is zero. In that case, the mgh is a change in potential energy. Now, in that case, the mgh is going to be the change in the gravitational potential energy. Back to the problem here. I exert a force that way. That force has to be exactly equal and opposite to QE. So that force has to be exactly opposite to QE. Okay, so in magnitude, it's got to be equal to QE. So the magnitude of that force is QE, and I go some distance here, x, and so, or we can just call that d for the distance that I traveled. And so we would say that the work done, okay, if I'm going at constant speed, then that's going to be the change in potential energy. So that's going to be the integral of QE dx. So in other words, that's going to be QE times d. Okay. And so this gives us this idea that we did work there. Okay, moving this. Okay, so suppose the electric field is from like a dipole or something, and so it's curved. And so I'm going like this, so that means the electric field is changing strength and changing direction. So that means that the work done, this is going to be the change in potential energy, is equal to integral of f dot ds. Okay, now, in this case, the f that I apply is vector is going to be minus QE. Okay, so it's got to be minus QE because I'm going opposite the direction of E. Okay, so now in vector form. Okay, so I could then say this work, which is the change in potential energy, is going to be the minus integral QE dot ds. Pull some of these things out. So this is going to be minus Q integral E dot ds. Okay, the Q is not going to change, and it's a scalar. It comes out of the integral. So there we have this change in electrical potential energy. It depends on the charge. It depends on the electric field and ds. Well, it's nice to think about it this way, but there's another thing we can look at, and that is that we can imagine, again, thinking back to physics 1, you have something sitting on a table here. You have something sitting on a table, you have another object sitting on the ground, and you might have a little ramp here on the table, something sitting up here. You know that the potential energy is different between the two. You know that the one closest to the ground has the least potential, that's the middle, that's the highest. Okay, but the potential energy is going to be mgh. Well, the G and the H are external variables. The only thing you're changing is the M. You change M's, you change it. If you double the M's, you just change the energy. So the G and the H are defined by your setup in the lab. And so we could talk about the energy per mass. Well, it turns out that we almost never do that in Physics 1, but we actually do that a lot in Physics 2. Rather than talking about the change in energy for each charge, because that turns out not to be very useful, because when you move charge from one place to the other, you're normally moving enormous numbers of electrons. And moving enormous numbers of electrons, there's no way of keeping track of each one. So what you do is you define something that is the change of energy per charge. And that's going to be equal to minus this integral E dot ds. And we're actually, technically you put a little symbol in there to indicate you're integrating right along that line. But this right here, the change in potential energy per charge, we actually give a separate name to, and that is the electric potential. And so that's equal to this integral E dot ds. Okay. The symbol for electric potential is V. Well, we can't use E, and we don't want to use P, and calling EP would just be kind of confusing, so we use V. Well, why V? Well, because the unit of electric potential is going to be a joule per coulomb, which we define to be a volt, after Alessandro Volta. And so that is our definition right there. Volt is a joule per coulomb. Okay. So volt, a joule is a kilogram meter squared per second squared divided by coulomb. So this is going to be a kilogram meter squared per coulomb second squared. Okay. And again, as a student, I found this just really annoying. Okay, because it's just very awkward. Okay, it gets even more awkward because it turns out in the SI units, instead of defining charge, the SI unit is a coulomb per second, which is an amp. So that means this is going to be a coulomb meter squared second per amp second cubed. Okay, kilogram meter squared per amp second cubed. And so that is a volt. Okay, and that will come into us later because we're going to start talking about voltage and electric circuits. And so in that case, we need to know the amp, which is a unit of electric current, and how we get that from the voltage. And so that's why there's another way of keeping track of the units. When I was a student, keeping track of the units was a major problem in Physics 2. Okay, it is very important you keep track of units. If you're doing a problem and the units do not work, that means you have a 100% chance of having done the problem wrong. Frequently when I'm grading tests, that I can see, okay, you're trying to do something, but you did something silly and the units don't even work. Like you multiplied coulombs times seconds and got amps. No, you divide to get amps. So that means that automatically your equation's totally wrong, and you could have caught that. You could have caught your mistake. You might have forgotten, to divide or something. You could have caught the mistake if you had been keeping track of the units. So quite frequently when I grade exams, I keep making this comment, watch your units. Because if you had been keeping track of the units, you would have seen it was wrong. Okay, so that means that you got to be able to keep track of units, but now the units are way more complicated than they were in Physics 1. In Physics 1, you basically had kilograms, meters, seconds, you had newtons and joules and watts, and then all combined these things together, and it was pretty straightforward. Now it's not so straightforward. So when I was a student, I actually took a sheet of paper and I filled the entire sheet of paper with units and what they were equal to in terms of other units. And that was not a big deal for Physics 1 because you had newtons and joules and watts, and at that point kind of ran out of things, okay? But in Physics 2, you have this huge other amount of units that all relate to one another. By the way, the units of electric field. We've been using the units as a Newton per Coulomb. A Newton per Coulomb is, now what is a Newton? Okay, a Newton is a kilogram meter per second squared, okay, per Coulomb. Okay, and so if I multiply top and bottom, kilogram meter squared per second squared divided by Coulomb meters, then that is a volt. So that means a Newton per Coulomb is a volt per meter. Okay. Now, we've been using Newton per Coulomb as electric field units, but starting in chapter 24, your book switches to volt per meter for electric field units. And a volt per meter is actually exactly the same thing as a Newton per Coulomb. So again, just keeping track of your units helps an awful lot.